Hello, and welcome to the University of Washington, home of the Husky Robotics team. We are an entirely student-run organization, and over the past year we have grown from 8 members to over 30 dedicated members. We strive to provide students with the opportunity to learn skill sets and apply them in real-world settings. This video is designed to show you our team structure and how we divide our work. Then we're going to go into more specifics of the subsystems and how it's designed to accomplish each task.
Here at the Husky Robotics team, our team consists of 2 sectors, business and engineering. Our business team focuses on public relations, and our engineering team focuses on building the rover. We take anyone regardless of their background, and we provide workshops such as CAD, electronics, and programming. This year, we hosted a BattleBot competition to help introduce new members to the robot building process. They worked on designing, building, and testing their own robots. We will now introduce each component of the rover and how they will complete the given tasks.
Hey there. The electronics on board our rover have been designed to reliably supply power to our systems, communicate with our base station, and survive excessive vibration. For power, we're using 5 DC-DC power converters from Murata, the FRC power distribution board, and a 24-volt lithium polymer battery. For communications and controls, we're using multiple Arduino microcontrollers and Ubiquiti antennas. To protect our electronics from rover vibration, we're using Anderson power pole wire-to-wire connectors and Phoenix contact lever actuated terminal blocks to ensure that all our connections never detach. All the electronics on the rover have been overspecified by 25%, so we are confident that our systems will perform in any circumstance.
Last year's rover design was significantly overweight, so this year we made our chassis out of sheet metal. We designed our chassis in Autodesk Inventor and sent the part files to ProtoCase for manufacturing. Since the premise of the challenge is to design a rover that will be operated by colonists living on the Martian surface, we don't need to worry about the lag in communication time that rovers controlled from Earth experience. This means the human driver can make course adjustments in real time. We chose a tank-based chassis over a rocker bogie suspension system because we want superior speed over precision movement. Our chassis uses a pneumatic suspension system to minimize shock to our rover as it navigates difficult terrain. Our rover is capable of driving off a 1-meter drop at full speed without damaging any of the sensitive equipment on board. Our rover and base station communicate using a pair of Ubiquiti transceivers, one on the rover and the other at the base station, mounted on a pan tilt system that can turn the 360 degrees around and 45 degrees above and below the horizontal. We utilize the GPS coordinates of the rover and base station to make sure the 2 devices are always pointing towards each other.
For the science station, we intend to have 2 different tests running at the competition's launch. The first test will be a pH test using a flat pH sensor. This pH sensor is allowed to measure the pH of semi-solids as opposed to aqueous solutions given by any normal pH sensor. This is important to us because it means that we don't have to bring as much water with us onto the rover during the competition. The pH sensor will be mounted onto this turntable and is capable of testing 6 different samples. Our next sensor is going to be the humidity sensor, which senses the relative water to air content. A relative water to air content of pure water is going to yield us 100% humidity. The next would be 0% for an absence in water. As far as the interpretation of data goes, we're looking for a pH below 12 because anything above that is unconditionable for conditions on life on Earth. So it's safe to assume that anything above 12 will be inhospitable on Mars as well. As far as the humidity goes, we're trying to test for water activity above 0.61. This is because, like the pH, anything on Earth has a tolerance of anything above 0.61.
The software for controlling the rover has been designed to be durable, adaptable, fast, and extremely lightweight. Our software team has worked to ensure that no single element of the control system is irreplaceable and that astronauts can quickly, easily, and inexpensively replace any point of failure. This is accomplished through a minimalist on-rover control system which uses only commodity microcontrollers and networking equipment to get the job done. By moving heavy computation off of the rover and onto the base station, the control system can be made highly configurable without risk of interfering in crucial low-level controls operations. Direct motor control loops and timeouts are handled on the rover, while higher-level control operations such as kinematics and GPS mapping are handled safely back on base station computers where they present no risk to vital rover functionality. Additionally, placing only the lowest level of controls on board allows for the use of microcontrollers that are cheap, easily replaceable, and quick to start up. For all these reasons, our control system would be perfectly at home in a Mars rover operation.
This year, we tried to make our arm a better fit for the task of the competition and our unique chassis design. The arm is composed of three main sections. The first section of the arm is responsible for the larger movements. The section contains a rotating base and two vertically oriented joints. The two joints rotate in almost complete circles, giving us a lot of flexibility in our controlling. It also gives us the ability to both reach down to the ground and all the way up to 1 meter if need be. All of the joints are powered by worm drive motors with about 2.5 Newton meters of torque. The motor output is geared up to enable the arm to lift 5 kilograms to a horizontal position relative to the chassis. The second section serves a purpose similar to a wrist, rotating the gripper to the correct orientation. The wrist is composed of 3 180-degree high-torque servos. The final section of the arm is the gripper itself, which uses a small DC motor on a worm gear to open and close its fingers. The worm gear increases the motor's relatively small torque and also ensures that the fingers are not back-drivable in an overloading situation. The fingertips have a thin layer of foam covered with rubber to ensure a more secure grip on uneven surfaces. All of the joints on the arm either have a mechanical limit switch or angle limits in code to prevent the arm from tearing itself apart. The arm also has one camera mounted on the second joint to give a closer view of the wrist for proper alignment. For the soil sample, we replace the gripper and final servo of the arm with a simple excavator-style scoop. The scoop is long enough to dig down to retrieve soil, but from below the 5 centimeter mark, without the rest of the arm impacting the ground. After the soil is retrieved, the arm rotates up and drops the soil into a funnel, which directs the dirt into one of the 6 capsules on the science station for testing.
We would like to thank TAP Plastics, Janicki Industries, Interlocks, Protocase, Wells Fargo, and the Mechanical Engineering Department and Aeronautics and Astronautics Department at the University of Washington. We would also like to thank all of the people who have contributed to the team through our USEED crowdfunding campaign. In particular, Mark Edson and Amr Awadallah. Thank you very much for all of your support. We would like to thank the judges and the Mars Society for this amazing opportunity. We have learned so much from this experience and have gained knowledge, skills, and lifelong friendships. We look forward to seeing you in Utah.